Today, we're diving into a technology that feels like it's been pulled straight out of science fiction. It's something that has the potential to literally change everything about how our world works. We're talking about superconductors.
Now, you might have caught the headlines recently about a material called LK99. And for a minute there, it really seemed like we'd done it, like scientists had actually discovered the holy grail of physics, a superconductor that could work in just normal, everyday conditions. The excitement was absolutely electric.
Well, as it turns out, LK99 wasn't the giant leap we were all hoping for. But here's the thing. That little flash of excitement, that what if, totally lit a fire under the global race for this tech. The quest for a room-temperature superconductor is more intense now than it has ever been. So let's talk about what a world powered by this technology would even look like. I want you to imagine a world with trains that literally float, power grids that are perfectly efficient with zero wasted energy, computers that never ever overheat. That's the promise of superconductors. It's a world without electrical resistance.
So what is a superconductor, really? Okay, think of electrical resistance like friction. When electricity moves through a normal wire, like copper, the tiny electrons are constantly bumping into atoms. That creates friction. That friction wastes energy and creates heat. It's exactly why your phone charger gets warm. Well, a superconductor is a material that has zero friction for electricity. None. The power just glides through it perfectly, with absolutely no energy lost along the way.
I mean, the difference is just night and day. A normal conductor, by its very nature, is inefficient. It's always losing some energy as heat. But a superconductor, it's literally perfect efficiency. Every single bit of energy that you put in one end comes out the other.
Okay, so if this technology is so incredible, why isn't it everywhere? Well, this is the big catch. For a material to act like a superconductor, it has to be ridiculously cold. And I mean cold. We're talking temperatures near absolute zero, which is colder than deep space. And achieving that requires some seriously complex, expensive, and energy-hungry cooling systems.
But, and this is a big but, even with that huge cooling challenge, the magic is already starting to happen. We've developed a class of materials called high-temperature superconductors, or HTS. Now, high temperature is a bit of a funny term here. They still need to be cooled with liquid nitrogen to around minus 200 degrees Celsius. But they're making it possible to upgrade our world right now, and it all starts with our power grid.
Take a look at this number, 3,000 gigawatts. That is the amount of renewable energy, from solar, from wind, that's already been generated and is just waiting to get connected to power grids all over the world. That's a mind-boggling amount of clean energy, just sitting there, unused. It's 5 times the entire global solar and wind capacity we added back in 2022.
So you see, the problem isn't making clean power. We're actually getting pretty good at that. The real problem is moving it. Our grids, many of which are over 50 years old, just can't handle the load. It's like a global traffic jam for electricity. We have this outdated infrastructure that can't get the energy from where it's made to where we all need it.
And this is exactly where HTS cables come in to save the day. They solve this gridlock problem in 3 really crucial ways. First, they are unbelievably power dense. They can carry 10 times more electricity than a copper cable of the same size. That means we can just slot them into the existing underground spaces we already have. Second, they can send all that power at lower voltages. This is huge because it means we need fewer of those big, bulky, expensive substations cluttering up our cities. And third, because they're buried underground, they're safe from weather, from damage. They just create a way more stable and reliable grid for everyone.
All right, now let's switch gears because this technology is set to revolutionize more than just our power grids. Let's talk about transportation. Superconductors are the key that unlocks a whole new era of travel, mostly through something called magnetic levitation, or maglev.
The speeds we're talking about here are just incredible. You know, a local urban maglev might cruise along at about 110 kilometers per hour. But then look at the Shanghai maglev, 431. And then you have Japan's SC maglev, which has hit a record-shattering 603 kilometers per hour. That's faster than a lot of planes are going when they take off.
So how on earth is this possible? Well, the secret sauce is getting rid of friction. The train literally floats above the track on an incredibly powerful magnetic field. With almost no resistance, you can not only hit speeds that rival air travel, but the ride is also super energy efficient and unbelievably smooth.
Okay, so there are basically 2 main flavors of this tech. You've got EMS, which is what they use in Shanghai. It uses magnets to attract or pull the train up towards the track. It works, but it needs constant computer adjustments to keep that tiny gap stable. Then you have EDS, which is what Japan's SC maglev uses. It uses repulsive force. It literally pushes the train up and away from the track. This makes it way more stable at high speeds and gives it a much larger and safer gap to float on. That's why it's the go-to for these ultra-high-speed systems. Okay, so we can build perfectly efficient power grids in trains that go over 600 kilometers an hour. The question is obvious, right? Why isn't this tech everywhere? Well, this brings us back to the big reality check, the high cost of cold.
It really boils down to 4 major roadblocks. First up, the economics are just tough. The superconducting materials themselves, these complex ceramics, are expensive to make. Then you have to add the enormous cost of the cryogenic cooling systems to keep them running. Then you've got the technical headaches. The cooling systems are bulky, and the materials themselves can be brittle and really hard to manufacture on a large scale. Plus, you can't just plug this stuff in. It requires huge, expensive overhauls to our existing infrastructure. And finally, we're still figuring out how durable they are long-term out in the real world.
But, and this is important, despite all those challenges, we are standing at a tipping point. Decades of research are finally starting to pay off, and the future for this technology is looking brighter than ever. So, what's changed? Well, the fundamental science is no longer a question mark. It's proven. The materials have gotten much, much better. And with the skyrocketing demand for clean energy, for power-hungry AI data centers, and for high-speed travel, the business case for superconductors is suddenly making a lot of sense. It's never been stronger. We are finally moving from just small pilot projects to the edge of large-scale deployment. And that really brings us to the final thought here. This revolution in how we move and use energy, it's not some distant sci-fi dream anymore. It's right on our doorstep. So the fundamental question has totally changed. It is no longer a matter of if superconductors will reshape our world, it's just a matter of how quickly we're going to make it happen.